Okay, today's lecture we are going to start the last part of modern physics, which goes by the name nucleus. Nucleus. So we are going to go deep into nucleus today. It might take one more lecture also. So let us see how far we go. So the nucleus, it consists of protons plus neutrons, and it occupies very small size of atom. Very small size of atom. See, the nuclear diameter or radii, the nuclear radii for all the elements are of the order of 10 power minus 15 meters, which we call as 1 Fermi. So the nuclear radii will be 1 Fermi, 1.5 Fermi, 2 Fermi, 3 Fermi and so on. Okay, it is of the order of 10 power minus 15 meters. This 10 power minus 15 is a very small number. So a convenient unit to represent that is Fermi. 1 Fermi is 10 power minus 15 meters. That is the idea. Now, having said that, this nuclear size is very small. How did this conclusion has been arrived at? That conclusion has been arrived at from Rutherford's gold foil experiment. So you see, Rutherford took a gold foil. So suppose this is the gold foil having some thickness. Then Rutherford bombarded them with alpha particles. What are alpha particles? Helium atom with the 2 electrons removed. He, 2 is the atomic number, 4 is the mass number. Normally we write atomic number at the bottom, mass number at the top. But the electrons have been removed from this helium. So essentially this is He2 plus. So this is what is called an alpha particle. This is what is called a alpha particle. So alpha particles are quite heavy compared to electrons, because the mass of proton itself is 1836 times mass of electron, and in alpha particle there are 2 protons plus 2 neutrons. So roughly this is 4 nucleons, 4 times 1836 times mass of electron. So this is almost 7000 times or 7500 times or whatever mass of electron. That means when alpha particle and electron collide, it is like elephant kicking football. Nothing will happen to elephant, football will fly away. So when alpha particle goes and collides with any of the electron of the gold atom, okay, so alpha particle will not be deviated much, but the electron will be kicked off, or it will be going this way and that way. But if alpha particle encounters the nucleus of gold, which contains many protons and many neutrons, then alpha particle should be deviated. So in fact, if nucleus occupies very large space, suppose there are zillions of atoms here, and all these nuclei, suppose if I show them like this, jam packed, then when this alpha particle goes, it should rebound, because gold nucleus is much superior to alpha particle. Electrons are nothing, peanuts. But what is observed is, alpha particles, most of them go undeviated or very slight deviation. That means they are not encountering the gold nucleus. Why they are not encountering gold nucleus? Because there are so many gold atoms with so many gold nuclei. The point is, the gold nucleus, the nucleus occupies a point size. So it is very difficult for alpha particle to exactly go and encounter the point. Most of the time it is going through the empty space between the atoms. So what you call as a gold metal block, actually when you look at it in an electron microscope, lots of empty spaces are there. There are very small dots called nuclei, surrounding which some electrons are rotating here and there, or moving here and there. So most of the atom is empty, hollow space. So what you are calling as a gold metal block, most of it is empty, hollow space. Just here and there some dots are there which are called nuclei, surrounding which electrons are there. So the point is, nucleus occupies a very small size. That's why 1 in 1 million alpha particles tries to collide with nucleus and comes back. So in Rutherford's experiment, if this is the gold foil, he sent million alpha particles, of which most of them went through, some just got deviated in some manner. Only one in 1 million turned 180 degree. Why? Because it was kind of bombarded exactly along that point mass called nucleus. So it was trying to go exactly and hit the nucleus, and the nuclear protons and neutrons repelled this alpha particle so strongly that in this collision it turned back. So this is what is happening. So that's why the nuclear size is very, very small. It has been estimated that the nuclear size is of the order of 10 power minus 15 meters. This nucleus contains protons and neutrons. Now let us talk about the forces inside the nucleus. So the forces inside nucleus. So if I show nucleus like this, it's a very small size, but I am showing it here as a sphere, let us say, with protons and neutrons inside. So protons I am showing like this, and neutrons I am showing like that. So in some fashion. So nucleus consisting of protons plus neutrons. Now the thing is, there are electrostatic repulsions between these protons. So the proton, which I am showing with the shaded color, each of these protons repels the other protons. So these repulsions are very, very strong. Electrostatic force is very strong. So this proton is repelled, it is repelled. So all these protons will try to break away and run away to infinity, because there are huge repulsions between protons. But we see most of the nuclei are stable. Okay, most of the nuclei, for example, if you take hydrogen nucleus, it is stable. Of course, hydrogen nucleus contains only just one proton. If you take deuterium, one proton and one neutron, okay, still there are no two protons, so no repulsions. But if you take helium, lithium, beryllium, boron, in helium there are two protons. Still, even though there are repulsions between these protons, the protons are not flying away. The nucleus is stable. Similarly, if you take beryllium, boron, carbon, nitrogen, oxygen, more and more protons are there. But even though there are repulsions, they are stable. So, in spite of repulsions, these protons are together, means there is some other attractive force between these protons. Not only between protons, between any two protons there is an attractive force. Between proton and neutron also there is an attractive force. Between two neutrons also there is an attractive force. This attractive force is called nuclear force. This attractive force is called nuclear force. We will see about this nuclear force shortly. So there is electrostatic repulsion. There is electrostatic repulsion between protons. Neutrons, there is no repulsive force because neutron is neutral. But there is an attractive force between proton, neutron, proton also there is an attractive force. Neutron also there is an attractive force. This attractive force is called nuclear force. It's very short ranged. It's a short ranged force. Okay, this nuclear force comes only when the distance between two nucleons is 10 power minus 15 or less. 10 power minus 15 meters or less. Okay, it doesn't come at very great distances. So nuclear force is very strange force, short ranged. We are going to study about this soon. But let us talk something about the density of all the nuclei that we see. Very important discussion. Density of nuclei. See, what this means is, you take any nucleus which contains at least two or more nucleons. So for example, you can take deuterium, you can take helium, lithium, beryllium, boron. If you take this nucleus, the number of nucleons in certain given volume, suppose if I show certain volume, the number of nucleons in that volume in any nucleus is going to be same. You fix the volume, you will always see in that volume same number of nucleons for any nucleus. Okay, you can take iron, you can take aluminum, you can take copper, whatever nucleus you take, number of nucleons in certain given volume is same. Okay, number of nucleons, you can say number of nucleons per unit volume is constant. Okay, and roughly the neutron and proton mass are almost the same roughly. So the mass per unit volume is constant. Number of nucleons per unit volume is constant, means mass of the nucleons per unit volume, mass of nucleons per unit volume is constant. What that means is density is constant. So for all nuclei, density is going to be constant. Okay, this is a very important thing. So density of nucleus is constant. From this I can say density into volume 4 by 3 pi r cube of the nucleus. Density into volume is mass of the nucleus, which is proportional to mass number. Okay, mass is proportional to mass number. Mass is proportional to number of nucleons. So I can say rho into 4 by 3 pi r cube is proportional to mass number. Okay, from which I can say r cube is some constant into mass number. I can write like that. Why? Rho is a constant, 4 by 3 pi is a constant. You can have other constant here. So send rho and 4 by 3 pi to other side. So r cube is proportional to mass number. R cube is some constant into mass number. So I can write r is some new constant into mass number. I can write it as a power 1 by 3. I am taking cube root on both sides. R cube is some constant into mass number. I call it as a. Mass number I write it as a. Atomic number I write it as z. Okay, so generally the terminology is z we use for atomic number, a I use for mass number. Okay, any element that you want to write, you write it as x, mass number, atomic number. You write like this. This is the terminology. Okay, so r cube is given by some constant into mass number. So r will be some new constant into mass number power 1 by 3. This new constant should have dimensions of radius. Dimensions of radius means that is also in Fermi. So we say r is some constant r naught a power 1 by 3, where this is mass number. That's of course dimensionless. This r naught has a value of roughly 1.2 Fermi. 1.2 Fermi. So radius of any nucleus is given by r naught, whose value is roughly 1.2 Fermi, into mass number power 1 by 3. This is a very important idea. How you are getting this relation? By assuming that the density of the nucleus is constant, which is roughly correct. Okay, this is not debatable. This is correct. Density of every nuclei that you see, because after all, what does nucleus contains? Just protons and neutrons. Any nucleus that you take, iron or copper or aluminum, it consists of only protons and neutrons, and they all arrange in certain way, and roughly the proton and neutron size, I also say it is same, their mass is also roughly same. So I would say the number of nucleons in certain volume for any nucleus is same. So density is constant. So once density is constant, you can say the r cube is some constant into mass number. Density is not variable, na? So when it goes to other side, it merges with the constant. Take density to other side of this expression, it merges with the constant. So r cube is some constant times mass number. So r is some new constant into mass number power 1 by 3. That new constant has got dimensions of radii, because mass number is just a number. So r is some r naught a power 1 by 3. What I am saying by this relation is, as you go to elements with more mass number, okay, the radii will be more. Obvious, because more mass number means more number of nucleons. More number of nucleons means the radius size is increasing, but density is constant. Number of nucleons in unit volume, you take unit volume anywhere in the nucleus and find the number of nucleons in that, it is going to be same. Okay, so this expression is very important. Just as an example, let us see for hydrogen nucleus, its radius is given by R is R naught into A power 1 by 3. R naught is 1.2 Fermi, let us say. Okay, this mass number A for hydrogen is 1 power 1 by 3 or 1.2 Fermi. This is the radius of hydrogen nucleus. Same thing, if I take aluminium nucleus, its radius is given by R naught A power 1 by 3, that is 1.2 into mass number for aluminium is 27, right, or 1 by 3, 1.2 into 3, 3.6 Fermi. So you see the radius of aluminium nucleus is more compared to that of hydrogen nucleus. This is logical because in aluminium there are more nucleons, so the size of that nucleus is going to be more. So this is one thing which is very important, this relation. Now let us talk about the nuclear force. I was telling you about the nuclear force. Okay, so let us talk about the nuclear force. Nuclear force is very strange. We do not know about the nuclear force completely even now. So the nuclear force is very strange. First of all, it is attractive force. It is attractive force. Second, it is short ranged, very short ranged. Okay, electrostatic force or electromagnetic forces are very long ranged. If we have two protons separated by 1 kilometer also they can exert force. But nuclear force is very, very short ranged. Okay, it operates within a radius of some Fermi, that's it, within 10 power minus 15 meters. If you slightly increase the distance, nuclear force will disappear completely. That's very strange. So it is a short ranged force. It is not dependent on charge. It is not dependent on charge. That means if you take two protons at certain distance, there is nuclear force between them. If you take two neutrons at the same distance, there is nuclear force between them. If you take a proton and a neutron also, there is a nuclear force. So it doesn't care whether the subatomic particle has charge or no charge. All it does is it acts when these two subatomic particles, when these two nucleons are separated by a very small distance. Okay, some people have suggested certain theory for nuclear forces. The most famous one is Yukawa's theory, which is very strange. So Yukawa says nuclear force is coming into picture because these nucleons are kind of exchanging some particles between them or exchanging something between them. For example, let us say there are two football teams, both are enemies. Football team 1 and football team 2, both these are enemies. Let us say enemies means if they see each other on roads, they are going to take knives and kill each other, let us say. But in the football ground, they are coming together. Why? Because there is something called a ball and each one wants to take the ball and put it in the goal post. So even though these two are enemies, they are coming closer, you see. Normally they would like to live kilometers away apart. But the moment a football tournament comes, these two enemies are coming together and playing football. Means they are coming close. So you see, same way, these two protons, for example, normally they would like to stay very apart. They are, because there is a repulsive force, electrostatic force between two protons. But when they come very close, they are exchanging something like a ball. Something. We don't know what it is. They are exchanging something like a volleyball tournament in which the ball is keeping the opponents close enough. Or you can say there are two dogs. This is the best example given in Yukawa's theory. There are two dogs. Okay, dog 1, let me call it dog 1 and dog 2. Both these dogs are bitter enemies. But then they caught hold of a bone. A bone. Half of the bone is in dog 1's mouth, half of the bone is in dog 2's mouth, and these two dogs are quarreling. So you see, normally the dogs like to stay very far apart, but something is keeping them together. What is it that is keeping them together? That is the bone. That is the bone. Half of the bone is in first dog's mouth and half of the bone is in the second dog's mouth, and this is keeping the dogs together even though they are bitter enemies. Similarly, these two protons, there is electrostatic repulsion between them, they like to be very far away, but something is being exchanged. There is some connection like a bone between them which is keeping them together. Okay, that operates only at a very small distance. For example, here also the dogs, the bone is very small, so at a very close distance the dogs are together. Okay, the bone cannot be 1 kilometer long. If such a bone was there, both dogs would be happy. One dog is 1 kilometer away from another, both would be biting the bone slowly and coming closer. But that's not the case. The bone is a very short length. So similarly here, at very short distance, something is being exchanged. I don't know what it is. That is what Yukawa's theory is, which is binding all these nucleons, the protons also together, the neutrons also together. Something is being exchanged continuously. So this exchange later they found out to be what is called muon, pi muon and mu muon and so on, and one gets converted to another and all that. So a proton can be converted to neutron and so on inside the nucleus. So neutron gives something to proton, proton gets neutralized and becomes neutron, neutron becomes proton. Number still remains same. For example, there is a proton and there is a neutron. This is proton, this is a neutron. So the neutron gives something to proton, this became proton now, that became neutron. Still the number is same, but some exchange is going on. Okay, at a higher level you will see even deeper things in particle physics. What is this particle which is being exchanged and so on. So that is what is keeping them closer. So this is about nuclear force. Short ranged, it is attractive force, and it is non-dependent on the charge. The nuclear force is same between two protons, same between a proton and a neutron, same between two neutrons also. Now inside the nucleus also, if we go a bit more deeper, inside the nucleus also there are nuclear energy levels. So inside the nucleus, just like you have atomic energy levels, so for example the electron can take certain energies when it is around the nucleus. Some energies are very less, you call them as lower energy levels. Some energies are very high, you call them as higher energy levels. And depending on the energy, the radius of the orbit also is changing for electron. Similarly, inside nucleus, now we are going inside nucleus, there are nuclear energy levels. It is best to show them by diagram. So the lowest energy level I will show it like this, the next higher energy level I will show it like this, the next higher energy level I will show it like this. I will come back to what these are. Each energy level, this is ground state, let us say. This is a first excited state. So we are talking now something inside the nucleus, and this second excited state. So inside the nucleus, so each state can accommodate 2 protons and 2 neutrons only. 2 protons plus 2 neutrons. Only that it can accommodate. This is the theory that is suggested based on experiments. So in the ground state, I can put 2 protons and 2 neutrons. If there is a higher proton, that means if it is atomic number 3 and one more neutron, I must go to next level. For example, if you take lithium, so it has got 3 protons. 2 protons are already in the ground state. One more proton, where will you keep? You will keep here. And if there is one more neutron, you will keep it there. Or if there are 2 more neutrons, you will keep it there. Like this. So each energy level can accommodate 2 protons and 2 neutrons. If there are more protons coming into the picture, you have to accommodate them in the higher energy level. Okay, these are what are called nuclear energy levels. Now a question might come, sir, are there compartments like this inside nucleus? No, but I am talking about the energies. So if there are 3 protons inside nucleus, 2 have lesser energy, 1 has slightly greater energy. Okay, that is the meaning. In what form is this energy there? I do not know. The protons might be moving in certain way, or they might be rotating. We do not know how this energy manifests. But this is how the nuclear energy level is. Now for example, suppose if I take a hypothetical nucleus which I am constructing using 4 neutrons. See, first of all, a neutron itself, a single neutron is unstable. Given some time, it will break into a proton plus electron. This is what is observed. But why can't we have a nucleus just with one neutron? Okay, neutron is unstable for some reason. What about 2 neutrons? 2 neutrons can make one nucleus. There is no proton, there is no electron. The nuclear force is binding these 2 neutrons. Is it possible? If it was possible, this would have been having an atomic number 0 if it is stable. But scientists have postulated 4 neutrons, tetraneutron. This nucleus could be stable, though it is not found in the universe, or maybe it is there, we have not discovered, or we have been unable to prepare in the laboratory. 4 neutrons, no proton, no electron. The nuclear force is binding these 4 neutrons together. Neutron, because there is no proton, atomic number should be 0. Okay, why is this not possible? The problem with such things is, it is explained with these nuclear energy levels. You see, if I take these nuclear energy levels, 4 neutrons means these are the energy levels where I am putting protons, these are the energy levels where I am putting neutrons. Now the thing is, if there are 4 neutrons, 2 neutrons can be accommodated in the ground energy level. The other 2 neutrons, there is no choice, you have to accommodate them in the upper energy level. Now what happens is, these neutrons which have higher energy, they will do something very strange. These neutrons give to electrons and they become protons. They are at higher energy level. These are neutrons, neutron and neutron. A neutron can give an electron a negative charge and itself become a positive charge, so that it can occupy this lower energy level. Similarly, this neutron gives an electron and occupies lower energy level. And suddenly what do you have here? You have 2 protons and 2 neutrons, which becomes the helium nucleus. So if you were to make this 4 neutron nucleus, immediately it would try to become a helium nucleus and achieve more stability. Why more stability? Because if it becomes helium, these neutrons can come to lower energy level. They become protons and they can come to lower energy level. Always, nature always follows this law, that it will try to minimize the energy. It will try to minimize the energy. It will try to reach a situation of less energy somehow. That is always the nature's idea, because less energy is more stability. Okay, so that is the fundamental principle with which nature works. So here also it is the same thing. So these, if you start piling up too many neutrons, these neutrons can give away electrons and become protons. Note that mass of neutron is slightly greater than mass of proton. Okay, so what happens is, the neutron can dissociate itself into, or break up into proton plus electron. Okay, and some mass is also lost, and that is converted into energy of the electron. We are going to see that later. There is a concept called binding energy. We are going to see that later. Now, mass of neutron is more than mass of proton. So neutron can become proton easily. More mass thing can become less mass thing. But in some cases inside nucleus, proton gets converted to neutron. Proton gets converted to neutron. What is this? What is this case? For example, I tried to make a nucleus with 4 protons. These are the nuclear energy levels. Okay, 4 protons. 2 protons I have accommodated here. 2 protons I have accommodated in the next energy level. So this, I am trying to create a nucleus, for example, which just has 4 protons, no neutrons, and let us say 4 electrons are orbiting around that nucleus. Since we are looking only inside the nucleus, we are not concerned with these orbiting electrons, which comes in an atom, which is the Bohr's model or any other quantum theory. We are only going inside the nucleus. Now again, this system is unstable. because you see there is a possibility that this proton can get converted to neutron and come to lower energy level. In fact, these protons emit positive charge, that is they emit what is called positron emission, and come to lower energy level. But there is a catch here. The catch is proton gives out positron, it becomes neutron, and neutron will jump to suddenly the lower level. It is good, but neutron has more mass than proton. Neutron has more mass than proton. So how can proton get converted to neutron? From where this extra mass is coming? Proton is there, it is giving out positron, a positive charged particle, so that it loses the positive charge and it becomes neutral, and it becomes neutron. So far so good, but neutron has got greater mass than proton. So how is this possible? So the possibility is very strange, and you will be surprised that the greatest genius in physics will come here again, and that is Einstein. These protons are at a higher energy level. Okay, so they have a lot of energy. When they come to lower energy level, some of this energy, not all, some of this energy gets converted to extra mass, which gets occupied as neutrons. Some energy is also lost in the form of kinetic energy of positrons, no doubt, but some energy is converted into mass. So you see, nucleus has a technology. This is a very important statement. Nucleus has technology to convert energy into mass. In fact, mass and energy are interconvertible. The famous E equal to mc square, we are going to use it in our discussion heavily down the line. Okay, when we are going to introduce the topic called binding energy and everything, this is very important. So nucleus, we directly do not have this technology. Suppose I gave energy to a block, kinetic energy, and I asked you, please somehow convert this kinetic energy into extra mass of the block. I do not have this technology really, it's very difficult for me. But inside nucleus this is possible. If there is energy for any subatomic particle like neutron or proton, it is possible, and the technology is with nucleus to convert this extra energy into mass. Somehow this is possible inside the nucleus. Okay, so nucleus is a very strange thing. So a proton in higher energy level can come down, and while coming down, the extra energy, some part of it can use it to increase its mass. Remaining, of course, it will give it to the positrons which are being emitted. So this is possible. So nuclear energy levels are very important. So nuclear energy levels, each nuclear energy level can accommodate only 2 protons, 2 neutrons. If there are more protons or neutrons, you accommodate them in the higher energy levels. Now certain things can be explained with this energy levels. For example, when you go to lower atomic numbers, elements with lower atomic numbers, elements with lower atomic numbers, forget about isotopes, isotopes are there, no doubt, but in elements with lower atomic numbers, generally number of protons equal to number of neutrons. Why? So that you see, if you have an element with 4 protons, just 4 protons, these 4 protons have to occupy, 2 of them have to occupy higher energy level. It is not stable. So generally the situation is these protons get converted to neutrons, and you have a scenario where you have 2 protons and 2 neutrons, so that the energy is less. Similarly, you will have 4 protons and 4 neutrons. Of course, if an extra neutron is there, 5, it will be accommodated in the next higher level. It cannot be accommodated here. It becomes an isotope, no big deal, isotope. But what I am saying is, in elements with lower atomic numbers, number of protons are same, so that first you can occupy the lower energy levels, then you can go to higher energy level. You can't have a situation where there are only neutrons, 1, 2, 3, 4, 5, 6, because you see the energy is increasing and increasing. So some of these neutrons will immediately get converted into proton and come to lower energy level. That's why you have stable elements with equal number of protons and neutrons, but that is with lesser atomic number. The problem is, as you go to higher atomic numbers, okay, number of protons is more, so what happens is electrostatic repulsions dominate. So too many protons is also not good scenario, because then there will be repulsions. Suppose if I have too many protons inside the nucleus, then I have to arrange the protons a bit farther. Okay, I cannot pack all protons in one place now. They have some size. So if too many protons, the size of the nucleus increases. When size of the nucleus increases, then what happens is the nuclear force is short ranged, so it cannot keep track of the edge proton. Suppose you take the proton here and proton here, the distance has increased now, so nuclear force is very weak there. If you keep increasing more protons, repulsions will dominate the nuclear force, so the system will break, the nucleus will break. So too many protons is also not good. So as you go to higher atomic numbers, that's why what nucleus will do, it will make sure that there are more neutrons than protons. For example, if you take something like nickel, its atomic number is 28, but mass number, it starts from 58. So atomic number, for example, I am talking about nickel, okay, iron, cobalt, nickel. Atomic number is 28, but mass number starts from 58. There are other higher isotopes like 59, 60 and so on, 60, 61, 62, 63. But you see number of protons is 28, but number of neutrons is 30 here. Already there is a discrepancy here. Why you can't have 29 and of course the atomic number will change if it goes to 29, but why the number of neutrons is more? Because if you have too many protons, again repulsions will be more. So if the number of neutrons is more, what happens is the protons can be kept a bit farther and neutrons can occupy, the protons can be kept farther and neutrons can occupy the distance between these protons, and somehow the nuclear force will still be able to attract and keep them together. Repulsive force you have tried to decrease it because you kept protons a bit farther. Okay, if everything is proton, then repulsions will be more. Some neutrons must be there. More neutrons must be there if protons is more, number of protons is more. Why? So that if number of protons is more, first they must be kept farther, because if they are kept nearer, the electrostatic repulsion will be huge. They must be kept farther, and the other space is occupied by neutrons, okay, in which repulsions are less, and they keep attracting these protons again due to nuclear force. Okay, this is the theory. It's a very complex theory. So at lower atomic numbers, protons and neutrons will be same, energy levels will be balanced. But as you go to higher atomic numbers, for example, if you go to something like arsenic, selenium, bromine, krypton, rubidium, strontium and all these, what happens is the number of neutrons is quite huge. The number of neutrons is quite huge. Okay. If you go to even higher atomic numbers, then the number of neutrons will increase even more, because if protons increase, repulsions will be too much. So there is a balance which is striken at higher atomic numbers. Of course, if number of protons is more, energy level will be balanced. Energy levels will be balanced. But then repulsions will also be high. So the nature chooses that let number of neutrons be more, even though they go to higher energy levels, even though the energy is increasing, but at least repulsions are decreasing. So you have to strike a balance now. So on one hand, nuclear energy levels say let the energy be least. On the other hand, repulsions are saying there are too many repulsions, so again we have to minimize them. So you have to strike a balance between these two. So it's a very complex theory. Very, very complex theory. Now let's come to our understanding of this binding energy. This is a very important concept. Many questions are given based on binding energy. So let us look at this. Binding energy. This is a very important concept. When two or more nucleons come together to form a nucleus, each of these nucleons give away a fraction of their mass which gets converted to energy and is released in the formation of nucleus. So you see what I am saying. When two or more nucleons come together, forget about hydrogen, it has only one nucleon. Start from helium, which has 4 nucleons. He4, 2 protons, 2 neutrons. Lithium, beryllium, boron. So when two or more nucleons come together and form a nucleus, each nucleon will say, whether it is a proton or a neutron, let us all contribute some of our mass. Let us decrease our mass a little bit and give this as energy and achieve more stability. This happens. So what I am saying, if you, for example, take helium nucleus and measure its mass, whereas if you take individually mass of proton plus neutron and measure this, individual mass of proton plus neutron, if you measure and add it up, 2 proton, 2 neutron, this will be more than mass of the helium nucleus. It is always found like this. Always the individual masses of protons plus neutrons is more when you add them than the mass of nucleus. That means you add mass of proton plus mass of proton plus mass of neutron plus mass of neutron. This will be more than mass of helium nucleus. Helium nucleus also contains 2 protons, 2 neutrons. Here also I am adding 2 protons plus 2 neutrons. But somehow mass of helium nucleus is found to be less. Why? When nucleons come closer and try to form nucleus, they give fraction of their mass and that gets converted to energy and released. This released energy is called binding energy, and that released energy leads to stability. I will give an example to understand this. Suppose 10 of your friends have purchased, or 20 of your friends have purchased lands side by side and you want to construct houses. After you construct house, you all 10 people will meet and say, let us make it a small colony. Let us construct a compound wall for this colony for more security. Let us employ some guards in the night time so that there is more security. Let us buy some dogs and even monthly let us spend some amount on their food and everything. So what are these 10 friends doing? They are contributing some money. Each will contribute maybe 2000 rupees as maintenance every month. And initially they'll also make an investment to build a compound wall for their colony and so on. So each person is contributing some money, okay, for more stability of the colony, for more stability. Similarly, when neutrons and protons come together, each of them will contribute to some mass somehow to attain more stability of this nucleus. Okay. Now, one more thing. If suppose these persons contribute too much money, suppose each person is contributing 4 lakhs initial investment, okay, on security, compound wall, and you also want to have some cameras everywhere in the colony, and you want to employ 2 guards with big salary to them and everything. So they are contributing huge amounts. Tomorrow they quickly don't want to leave their house. They don't want to sell it also because it is a high security zone. They have spent so much money, so they are more stable. Okay, these 10 friends, the point of their breaking away is very less because they spend more money. Whereas suppose if these 10 friends spend only less money, everybody gave only 100 rupees and said for security we'll employ some guard with very less salary, we are only contributing 100 rupees per month. Tomorrow one friend feels, hey, I am not very happy and I just want to sell away this house and run away. He will easily sell it because initially what was his investment? Very less. His investment in security and other things are very less. So he can any day sell off his his house or his land, his house, independent house, and go away to some other place. Okay, so because initially his investment is less. Similarly, when these nucleons come closer, if they give too much of their mass, that will be a very stable nucleus. If they give very less mass, okay, and that mass got converted into energy and released, tomorrow it's very easy to break that nucleus. So binding energy is a very important factor. So when nucleons come closer, a fraction of their mass is converted to energy and released. The more this energy released per nucleon, the more the mass decreased per nucleon, the more the stability. So first, to understand this concept, let us first see how mass and energy can be converted, how they are interconvertible. I am just going to give you only mathematical expression. I am not going to take you into relativity. Okay, so the thing is, we have this relation E equal to mc square. So if I take, for example, 1 kg of mass and completely convert into energy, the energy released will be 1 into c square, 3 into 10 power 8 whole square joules, which is 9 into 10 power 16 joules, 9 followed by this is too much of energy. It can destroy earth also. That's it. 1 kg of mass, if you completely convert it into energy, this energy is enough to completely destroy earth. But the problem is 1 kg of mass completely converting into energy is the problem. You may break it into subatomic particles, some subnuclei, part of energy can be released, but completely must convert into energy. Anyway, the masses that we are going to deal with in nucleus are not 1 kg. So generally we are going to look at another unit called AMU, a smaller unit which is called atomic mass unit, because this is convenient to measure the atomic and nuclear masses. So 1 AMU is 1.67 into 10 power minus 27 kg. You see this number? Very small amount of mass. For that I am giving a unit 1 AMU. So in atomic and nuclear world, masses are measured in AMU. In our world, masses are measured in kg. Okay. For example, you want to go to market and get mangoes. You will say, give me 1 kg mango, give me 2 kg mango. You will not say, give me 0.01 quintal. You will not use quintal, right? It is not convenient in it. Similarly, you will not say, give me mangoes in AMU. For that, what do you need to say? Give me 10 power 27 AMU of mangoes. 10 power 27 is a big number. You don't want to use that unit, you see. You want to use appropriate unit depending on your convenience. For example, the distance between Hyderabad and Delhi should not be measured in light years. It's a very bad unit. You should measure it in kilometers. You should not even measure it in centimeters. Distance between Hyderabad and Delhi is so many centimeters. It will be a very big number. Distance between Hyderabad and Delhi is some 1500 kilometers. That's very convenient. 1500 kilometers is very convenient. Saying in centimeters or millimeters is not convenient. Saying in light years is also not convenient. So you have to use the appropriate unit. So for atomic and nuclear masses, AMU is a very good unit. 1 AMU is 1.67 into 10 power minus 27 kg. 1 AMU, if you completely convert into energy, this mass, if you completely convert into energy, what is the energy released? What is energy released? Let us look at that. So 1 AMU is 1.67 into 10 power minus 27. So energy released is mc square, Einstein's famous equation. Mass here is 1.67 into 10 power minus 27. C square is 9 into 10 power 16. So this comes out to be I'll not multiply this. It's better I write it as 1.67 into 9 into 10 power minus 11. Is it right? 10 power minus 11 joules. We got it in joules. But it is convenient to express it in electron volt. Not only electron volt, million electron volt. First let's convert to electron volt. 1.67 into 9 into 10 power minus 11. To convert into electron volts, divide with 1.6 into 10 power minus 19. So this will become 931.5 into 10 power 6 electron volt. Okay, because this 19, when it goes up, it will become 8, 10 power 8. You write it as 10 power 6, and remaining, if you calculate, you will get it. So 931.5 million electron volt. You see 1 AMU, if you completely convert it into energy, mass is being completely converted into energy. Mass disappears, energy appears, let us say. So 1 AMU, if it completely disappears, it gives you 931.5 million electron volts of energy. Disappear means how? I don't know how it happens. One simple example of mass disappearance is radioactivity. Mass decreases and energy comes, radiation comes. Okay, nuclear fusion, mass decreases and energy comes. Okay, atom bomb, hydrogen bomb, all these are, mass is disappearing, energy is coming, which can destroy even countries, atom bombs and nuclear bombs, basically. So 1 AMU, if it completely disappears, you get 931.5 million electron volts of energy. So I can write 1 AMU is equal to 931.5 MeV. Very important relation. This is a very important conversion factor. So I am saying a equivalence between mass and energy. One atomic mass unit is equal to 931.5 million electron volt. So if you have the technology with you, you can take 931.5 million electron volts of energy, and somehow if you convert into mass, you will get 1 AMU. You will get 1 atomic mass unit. This is possible. Okay? At least theoretically. We don't have the technology. Nucleus has the technology to convert mass into energy and energy into mass. Particularly energy into mass, Nucleus has this technology. So this is very important. It is coming from equal to mc square only. So I took 1 AMU, which is 1.67 into 10 power minus 27 kg. I did mc square. I got energy in joules. I converted into electron volt. I am not happy with that also. It is coming out to be 10 power 6 EV. So I converted it into million electron volt. So the 10 power 6 is million. So it becomes 931.5 MeV. So 1 AMU, if you completely convert into energy, it is equivalent to 931.5 MeV, is a very important conversion factor. So we'll take a break here. This is one part of our lecture. After the break, we'll again continue.